Okay, so this will be part 2 of some assorted problems that involve finding the derivative of a function, um, understanding about curves and tangent lines, and all the stuff we've been doing recently. Okay, so let's start with this one because these problems are just assorted. If I don't sorted, I don't really have any introduction I want to give to it. We'll just take it problem by problem. But let's do this problem first, and I'll give a little bit of an overview of it, and then we'll go in and solve it. So suppose it goes like this. Find the value of k so that the curve has the given tangent line. So there's this curve, and its equation, its formula is incomplete. It says 3x squared plus kx plus 1. Okay? So the k is some unknown constant. It's some fixed number. It's not given, and it's up to us to figure it out. Okay? But this curve has this tangent line. All right? And so there's a certain value of k that would make them come together. In fact, there's a value of k that make them come together something like this. Okay, I'm not saying this is the actual picture, but here's a picture for me to get the point across to you regarding what we're dealing with. Okay, so yes, so there's the curve in pencil, there's the tangent line, and that's what they would look like together. They would meet at one and only one point. At that point, the slope of the curve and the tangent line are identical. So here's how it seems that we can set this up. There is a point that the curve and the tangent line both share. That means that their equations are equal at that point, meaning they have the same x value and the same y value at a certain point. But also, see the and right there? The slope of the curve is the same as the slope of the tangent line. So, okay, so see y is 3x squared plus kx plus 1. If we use our rules, y prime, being the slope of that curve, is 6x plus k. And then that would need to be negative 8, which is the slope of the tangent line. So we come down to solving this problem through solving those two equations. All right? So that's the overview. So let's get into the work now. So I need to do this. I need to solve 6x plus k is equal to negative 8, and this other one, 3x squared plus k times x plus 1 equals negative 8x minus 11. So this one says the slope of the curve needs to be negative 8 at this point. And this one says that the curve and the tangent line share that point. All right? So those are the assumptions that are built into the problem to say that this curve has that tangent line. So how about this? Let's so we've got two equations, two variables. The way that we normally solve that is we solve one equation for one of the variables and then we substitute into the other. So suppose that I want to solve for k. I think it'd be easy to do it like this. Let's solve this equation for k. And then I can put that in right here. All right? And then solve for x out of that one. And then once I know my x, I'll get my k. All right. So if k, according to this, is negative 6x minus 8, that would bring this way. 3x squared plus k, what's k? Negative 6x minus 8. X plus 1 equals negative 8x minus 11. Okay? All right, now let's try to work this out. It will take some simplifying. Let's see, I'll have to distribute this x in there. So I get negative 6x squared, say right here. I'll get negative 8x right there, plus 1, okay. I'll get negative 8x minus 11. Now, let me do a few things at one time. 3x squared and negative 6x squared. That'll be negative 3x squared. If I add 8x to both sides, this will cancel and that will cancel. If I add 11 to both sides, I'll get 12. So maybe I do this thinking I get a quadratic to solve. And I can solve this by the quadratic formula if I wanted to. I think it'll be a little bit easier to do this. Okay. Then I'll divide both sides by negative 3 and I'll get like that. And what do you square to get 4? You square 2 or negative 2. Okay, all right, 2 or negative 2. I could take plus or minus root of 4. That will get me my values of k. So look, first answer, suppose x turns out to be 2. I can put that here to find k. See, it says k equals negative 6 times the x minus 8. Well, suppose I find x to be 2. So that will be what? Negative 12 minus 8. That will be negative 20. Suppose I find x to be negative 2. I'll find out what k is right here. So that would be 12 minus 8, 4. So I'll get 2 answers, bottom line. All right. So given that the question says find the value of k, so that, okay, well then I have found it. There's actually 2 possibilities. K could be 4 and k could be negative 20. All right. Well, let me explain the relevance of the 2 possibilities. Now I've showed you how this is done. Most importantly, I showed you the setup and the algebra. All right. And I've got my answer right there. But let's look at it in a little more detail. All right. Okay, so here's the way this turns out. There's only one tangent line, negative 8x minus 11, but I guess we found 2 curves. Remember? You know, in my initial problem, that number was not specified. And I found that it could either be negative 20 or 4. So say you look at these curves, 3x squared plus 4x plus 20, plus 1, okay? That's with k being 4. And then 3x squared minus 20x plus 1. That's with k being negative 20. So one of the curves, this one, here's curve 1, is over here somewhere. And curve 2, this one, is over here somewhere. And that line does run tangent to both of them. It hits this one at negative 2, 5, and this one at 2 and negative 27. So that's why we could find 2 answers. Because depending on where this number is, it could put the curve here or negative here, and in either case, the tangent line would be applicable to it. All right, so that's why we found 2 answers, in case you're curious. Okay, but we did find 2 answers, and I want the setup, the starting point of the problem, to make sense. Okay, now depending on the nature of this curve, there might only be 1 answer. It just depends. And the algebra might be a little bit different, but you can set a problem that sounds like this up this way. All right. Okay. So let's look at one more thing. Talk a little bit about average versus instantaneous rates of change. Okay. So it's not hard for me to tell you the definitions of things. It's harder to explain what they mean. And I think that's generally true of math. That's my opinion. I understand not everybody in the world agrees with me, but I think often it's easier to do math than it is to really understand what you're doing. So here's an example. See if you agree with me. I have this function, f of t is equal to t squared, on the interval 2 to 2.1. That's like saying that t is somewhere between 2 and 2.1. All right? T runs from 2 to 2.1. The average rate of change of this function on that interval is f of 2.1, the function at the right endpoint, minus f of 2, the function at the left endpoint, over 2.1 minus 2. I hope that looks familiar. That's the same thing as the slope of the secant line through the curve at the points 2 and 2.1. It's just rise over run. So say we do all the math, the function is t squared, so that's 2.1 squared minus 2 squared. It ends up being 4.1. All right, that's what the average rate of change is on a given interval. Okay, what's the instantaneous rate of change at t is equal to 2? Well, it's easy for me to tell you that. It's the derivative f prime at 2. And that's what's f prime, right? F prime is t squared, so, or f of t is t squared, f prime is 2t. So I take, this part right here, quick note, f prime t is 2t, all right? And then I put 2 in there, it's 2 times 2, it's 4. All right, easy for me to tell you, I think. Now, 2 questions that follow this up. The answer to this, the average rate of change, or the slope of the secant line, whatever you want to call it, is 4.1, but the instantaneous at 2 was 4. The average from 2 to 2.1 was 4.1, but the instantaneous at 2 was 4. Why is that? Think about this question. I really want you to think about it. Why are the average and instantaneous rates of change so close? All right. You could think about it like this. We had this curve right here. The interval was t from 2 to 2.1. If you wanted to, you could think of that like there are points on the curve, 2 and 2 squared, which is 4, 1 point, and 2.1 and 2.1 squared, which is 4.41, another point. That average rate of change is the slope of this secant line through those points. We found it to be 4.1. But what is the derivative? The derivative is the slope of the curve. What did we found? We found f prime, the derivative at 2 is 4. That means that right here, this tangent line, or that little piece of the curve right there, has a slope of 4. Well, just look at the geometry of it. If these 2 points aren't very far apart, then the slope of the secant line through those points can't be too much different than the slope of the curve, say, at this point. The closer this point is to this point over here, the closer the average rate of change, okay, or the slope of the secant line, is going to be to the slope of the curve. Can you see why that is? All right? Yeah, 4.1 is just a tad steeper than 4. All right, so that's something conceptual that needs to sink in. Next thing, you notice how this was called the instantaneous rate of change. And it was easy for me to tell you what that was. It's just the derivative. Easy for me to tell you. But, we're understand calculus. We should think about why use the word instantaneous. That makes me think of time. And it should make you think of time too. Why does it make you think of time? Instant? What's an instant? An extremely brief moment in time, all right? So why would we use a word that makes you think about time? All right, well, okay, for this I need to give you a broader context. Let's say that, as can be done, if you learn some basic physics, you can learn how to track the movement of objects in free fall under the influence of gravity. And you can give their position at any time. It's possible. If you take some physics, you can learn to do that. But let's say that I have this function right here, and it gives you the position in feet on the number line at time t in seconds. So something's moving on the number line, and this function tracks its position or location at any time. Okay, so I drew the number line and I put my marks, and when t is equal to 0, 0 squared is what we get, so you're at the 0 mark. When t is 1, 1 squared is 1, so you're at the 1 mark. When t is 2, 2 squared is 4, so you're at the 4 mark. And when t is 3, 3 squared is 9, so you're at the 9-foot mark, and so on. All right? So just you have to grant me that. All right, that's what this function does. Something's moving. 1 second later, it's here. 1 second later, it's here. 1 second later, it's here. The average speed over, say, this time interval from 0 to 3, that's like the average rate of change, would be, well, you were at the 9-foot mark at the end of the interval. You started at the 0-foot mark at the beginning. and it took you 3 seconds. So that's 9 feet per 3 seconds. So that's 3 feet per second. Could that be accurate though? How accurate would that really be? Okay, so think about that. Maybe I need something more dramatic for you to question the accuracy of this number. So suppose I do an experiment. Anybody with a car can do this experiment. You've got your trip meter in your car and you've got a clock, and you can time how far you drive and how long it takes you to drive. So suppose I do this experiment and I drive 36 miles. So I measured that with my car's trip meter, and it takes me 45 minutes, which I measure with a clock. All right, these are just measurements. What is my speed? Somebody might be inclined to say, well, your speed is 36 miles and it took you 45 minutes. Let's say 0.75 hours, though. I think I like the units a little bit better. And I divide that out, 36 miles in 0.75 hours, and that turns out to be 48. Okay, 48 what? Miles over hours, 48 miles per hour. How accurate could that number be? You really don't know what was happening. I mean, if I drove 36 miles, there were times when I was stopped, and then I sped back up and I slowed down, and lots of different things happen. I mean, you know, you don't really think I was traveling at a constant 48 miles per hour. Even though it was possible, there's just not enough information to know that that's true. So this is the average speed, okay? And with that much time passing, I mean, this number is probably just not very accurate. Averages really don't tell us much. Like if we have a test and I say the average grade was 75, that doesn't really tell you much about what any one student's grade was, all right? So that's the limitations on the average. All right. So yes, like this is an average right here. That's the average rate of change I was talking about. It can't be that accurate. I mean, look, here you're moving kind of slow. 1 foot in 1 second. Then 3 feet in 1 second. And then 5 feet in 1 second. This thing's speeding up as it moves. Across that time interval, this is just an average. The instantaneous speed shrinks that time interval to almost 0. That's how we get an instant. All right? The instantaneous speed at t is equal to 3. T is equal to 3 is an instant. It is the derivative at 3. So you see, you know, what an instant is. A specific moment in time. Evaluate the derivative at that, and we'll get the speed at that moment. If we have a function that gives us the position or location of an object, the derivative will tell us the instantaneous speed. All right? Where again, you have to tell me the instant you're curious about. Okay, so that's a little bit of, you know, some philosophical and conceptual things about the vocabulary, but I want you to think about it in addition to being able to do the questions.